The next lecture is actually myself. We're giving a talk with Kang on nanotechnology-based laser metrology using frequency scanning interferometry. So I'll just upload the file. Okay, so today we're going to talk about using nanotechnology and aspects of lasers and so on and waveguides to actually how we can impact metrology. It's a bit of a shame this isn't coming up on here. So you know about optical coherence tomography. It's similar to ultrasound, where you bounce sound waves into a tissue and you're looking for the reflections coming back. In optical coherence tomography, using an optical beam. And what you do is you get optical reflections coming back, and you can, from that, reconstruct an image. We also use lasers for measuring distance. In the past, you might have seen, for instance, interferometry using a stabilized EE laser to measure distance, where the metric is really the wavelength of light. And by changing the distance, you count the number of fringes, and therefore you can detect the distance. And this is predominantly used in manufacturing, where you might use a CNM machine, and you look at tiny movements which you need to measure very accurately. The technology is moving on in metrology in the real world, and people are migrating from a fixed wavelength laser to a frequency tuned laser, where you change the wavelength. And now in an interferometer, like a Michelson, when you've got a tuned laser, you actually start generating what we call beat frequencies. And those beat frequencies now, depending on the chirp rate of the laser, dictate what the distance is. So you've got a different means of measuring the distance. So within that actually embodies a lot of new technology, which we need to work through and find that traceable standards and so on. And there are problems. There are problems using any interferometric device for measuring distance in the real world. So for instance, if you're working at Airbus or Boeing, you might be putting on the wings onto the fuselage or the plane. And what you find is the vibrations around you, which might come from a forklift truck, actually disturb the measurements. And so vibration is a limitation in the accuracy that you can achieve when you assemble a large plane. So there's lots of challenges in measuring distance. It isn't coming up my screen, I have to turn around. So just to recap, with optical coherence tomography, you've got two techniques. And what they did is, with the original concept of OCT, is you set up a Michelson interferometer, and you have a low coherence length laser, and you work at the near the zero optical path difference, where you get over a very short distance coherence, and that's generally referred to as white light interferometry. And then as you move one mirror in one arm of the interferometer, you're actually scanning through different layers in the tissue, because that's where now the optical path difference is zero. And so you're able to scan through the layers of the tissue, looking for those interference effects which occur close to zero optical path difference. And by doing that, you can actually reconstruct the various layers within the tissue, which correspond to going from continuous cells to fat cells and so on and so on. You can see the layers coming through on the OCT. Clearly, scanning a mirror is problematic. It takes time. So what people developed over the years was to use, we'll use a frequency swept laser. And because you might recognize from your A levels or undergraduate work that if you do the Fourier transform of the power spectrum by the Weiner-Kitching theorem, you actually get back to the autocorrelation function, which is exactly the same data that you achieve using the time domain. So when you work in the frequency space, do the FFT, you get the same information coming back. So that's what people migrated to, because it's quick and they can build up all sorts of scanning image, the A scan or B scans, which you saw in the previous slide. So key to this is actually achieving a swept laser source which has the right properties. So what I just tried to cover here, as technology's moved on, the limitation has been the lasers. You need to tune the lasers to get that spectrum. Some people use a superluminescent diodes, which basically just gives you all the wavelengths at the same time. And there's limitations there, because the more noise you've got in the system, the less you can penetrate into the tissue. So when you talk to experts in the OCT field, what they want is something which can be tuned wavelength-wise over, say, 30 nanometers at speeds which are around about 100 kilohertz. But what they really want is it to be narrow line width. And that's not really achievable with a lot of technology at the moment at low cost. Now, the narrow line width means you can actually penetrate deeper into tissue and reconstruct the images coming back. So if you want to go deeper, you need narrow line widths. So the key thing here is achieving a laser which achieves that. And that's what we showed some of the tolerances and accuracies coming through. Here you can see, you actually, there's a company called Optos, which is just in the Dumbarton area. They actually developed a technique for optical coherence tomography, OCT, and they scan a laser in the back of the eye. And you could well be using these devices now when you go into the opticians. And essentially, as you scan the laser back of the eye, you're actually doing the OCT measurement, and you're scanning the wave at the same time, and you produce a 2D image. And you can see there, and you can see within the retina, you can see if there's anything wrong in the layers behind the retina, which then indicates a problem, whether it's retinal detachment or conditions like that building through. So it's a very, very powerful technique. There are other applications for OCT. People are now beginning to use OCT. You can put a probe inside the body, and you can look at look through various organs and look at the composition of the tissues which surround, say, the liver, and look a little bit into the liver. And so, or you can look at the skin. You can see if, for instance, you've got a melanoma, which is a skin cancer, and you can actually measure that with the OCT, and you would see a difference in the tissue type by using OCT and so on. So over the last 10, 15 years, you will see that there's been a massive publications which have been building up in large volumes. And generally, when you got a large buildup of publications, you find the applications then for real applications in hospitals and so on, GP surgeries, will occur 5 to 10 years after that. That's just the gestation period for developing technology. So you can see there's lots and lots, and there will be more. There will be more as technology evolves. So a lot of time, is it the name of the company Axon? I worked in Silicon Valley for 5 years, and Axon was one of the companies which was developed at the time of the dot-com around 2000 to feed into the boom of the telecoms. And as it collapsed, all these companies, component suppliers, suffered, and they couldn't get any profit. So I think it was about 5, 6 years ago, Axon decided to switch their laser technology to not address telecoms anymore, but switch it over to a medical application. And they said, maybe we can use this laser, which is a MEMS-based tunable laser. So you've got a MEMS structure which tunes the laser. It's not particularly narrow line width, but it gives you the speeds. They switched over to from telecoms into medical, and all of a sudden they went from loss to profit. And now they're a major supplier into the OCT market for the high performance tunable laser approaches instead of the superluminescent diodes. And so they're doing really quite well, and they're on the east coast of America. So going on now, as I just demonstrated, one of the key things we need to look at is other ways of addressing the tunable laser with narrow line width. So this is typically the approaches that people might use. They are looking at approaches which use a diffraction grating, and then you feed light back into a gain chip. I call it a gain chip because it normally, if I didn't have an AR coating on the facet of the gain chip, it would be a fabric power laser. And so because I've put an AR coating on there, and I've shown a plain facet there, but sometimes it's actually wedged, it's angled, so that any reflections, even with an AR coating, is reflected into the cladding, so you actually eliminate any fabric pair modes that are created within the laser cavity itself. Now, by doing that, you feed light in from an external element, which then gives you a laser which has a much longer cavity length. And if you have a longer cavity length, what that means is you get a much narrower line width, which is what you want for a lot of applications in OCT and also in interferometry as well. And the reason for that is because it's all related around the photon lifetime in the laser. And the longer you make the photon lifetime, the narrower the laser line width. And so it goes as a function of L squared. You double the length of cavity, you get 4 times the narrowing of the line width. But you can see on the right-hand side, and I'm not sure what this is a blown up section. On that side there, you can see we've got a diffraction grating, which is fixed, and then we have a tunable mirror, which is picking off the wavelengths that are being diffracted off the diffraction grating. So you're picking off whether it's lambda 1 you want to laser at, or lambda 2. Now, you might remember back to school days where you use a trombone, and you change the length of the tube in the trombone, and you change the note. It's a standing wave pattern. Well, the laser is exactly the same. If we force a wavelength change by tuning that mirror, we need to change the length of the trombone, or in this case, the laser, so that we maintain the same mode. If it mode ops, it's game over. The device is no longer in measurement mode. So you can't allow it to mode op. So the way this is done, and New Focus has done this for decades. I've visited the plant in San Jose, and it's now New Focus. And essentially what they do is they use a pivot point. So as you change the angle of the tuning mirror, if you have a pivot point which is there, you rotate it by, say, 10 degrees, you get that movement. If the pivot point's there, the same 10 degrees is now that movement. So if you choose the right pivot point and the distance, as you change the angle to drive the wavelength change in the laser, you will then provide the right amount of change in the laser cavity length to maintain the same mode. Now you will look at this and you say, wait a minute, that pivot point is then critical to the stability of this laser over time. And it's a mechanical tolerance. So one, is difficult for the manufacturers to achieve that pivot point to get it right. And if it weighs over 6 months through continuous operation, it becomes unstable. So these 20,000 pound lasers from New Focus, if you use them continuously as we did in JDS Uniphase, they break down and you have to get them replaced and you have to get them reset up. So there's a major problem. If you want to use this type of laser in any commercial application, such as OCT or widespread into the interferometry field, you've got to solve the tunable laser problem. So what we've done, you'll notice here, is this very special laser. You'll notice I've got a periscope. There's the laser cavity on the right-hand side. It goes in through a filter, and then you've got a periscope. Now what I'm doing here, instead of using a diffraction grating to tune, and use an Ethlon. And we all know if you've got an Ethlon or Fabry-Perot and you change the angle, you change the transmission wavelength, which means you tune the laser. Right now it follows 2 nd cos theta. There's cos theta in there, which you know is 1 minus theta squared over 2. If you look at the periscope, this is a periscope which is used in submarines. If I rotate the periscope in sync with the Ethlon, I get exact tracking. So when I change the, say, the Ethlon by 1 degree angle, the periscope goes to 1 degree, you will get exact, if you get the distance of the periscope correct, you can get exact tracking of the cavity length. Mathematically, it is perfect, right? So there's no movement in the terms of the cavity from where it should be to achieve the single mode, mode-op-free behavior. And that 2 periscopes there is very cheap. It's 2 mirrors. The Ethlon is obviously in volumes. Well, we used to do wave lockers in JDS. They're like $50, so we can get the cost down. But the key thing is here, where's the pivot point? Before we had the pivot point in the New Focus, and it was ultra sensitive to the pivot point mechanical position. On this one, we don't care. It doesn't matter where we rotate. So there's absolutely no sensitivity to the pivot point. It's dependent on polishing a bit of glass, which is done at the beginning when you fabricate it. And as long as you don't repolish the glass, which you're not going to do in use, that will maintain that tracking for life. So it's completely robust and it'll be reliable. And that means all of a sudden, the components are cheap. We've got an approach which actually now allows robust tuning for life without any decay or degradation of the performance. But this is beginning to open up the opportunities. The patents on this have been assigned to, there's a patent we've got there. This has been assigned to Renishaw. Renishaw have taken on the patent, and obviously they're going to be developing it, presumably for a number of applications. It's low cost, it's cheap, and it can open up the market for metrology. And you can see there some prototypes we've made and some results on the right-hand side. Well, I do the time okay for that, burning through this. Yeah, I'm a chi, I can take as long as I want, all right? So you can see on the left-hand side, we've done a 3D model, AutoCAD, and you can see different demonstrations. This is what the PhD student has done this. You can see the periscope, simple piece of glass, 2 mirrors, rotate it, and it does exactly the tracking you want. It doesn't make any difference where the point of rotation is because it'll track regardless. So it's a very powerful technique, and we're in the course of obviously working with Renishaw. Now, I mentioned OCT, which requires ideally narrow line width, fast tuning, because then you can go deeper into tissue, so it opens up new markets. We also want to look at this application here. This is actually in Broughton in North Wales. And you can see you've got the wings and you've got the fuselage. Now, if you put the wings on the fuselage of a plane and one wing is longer than the other, then what you have is the planes in the air, without any other compensation, would start to rotate in the air. So what they do is, in practice, they actually try to, depending on which is trying to rotate, you actually adjust the speed of the engines to compensate, which is okay. But ideally, in Boeing and Airbus, they want to get it right at the beginning. So what they do is they use a number of reflectors on the wings, at which they measure all those reflectors and all those positions on the wing and the fuselage at the same time. Normal interferometry is a single distance measurement. So you can imagine you've got multiple measurements all being done at the same time. And this is a problem. And if you notice in the background there, you can see a forklift truck. So when they're trying to do this and do it accurately, they've got things banging around because it's a real environment. People are doing work. And it's a real problem. So they actually approached us and National Physical Laboratory in London and said, look, can we find a solution to this? So this is just showing you a standard microsynth interferometer. And you can see we've got a laser source and the beam splitter. There's your microsynth interferometer. And you create basically one mirror as a reference arm, and you shine the light up into space. And at each point where you want to measure, you have a target. It's just a small ball lens. And if you look at the mathematics, if you make the ball lens have a refractive index of 2, it becomes a perfect retroreflector to reflect light back from that position. So a small lens, index of 2, you get really good target positions. So on the left-hand side, I've shown one target. Because I spray the light into space, I could have 15 targets in that space, all on the plane. So the one instrument can now measure more than one target, which isn't possible with standard fringe counting interferometry. So if I got 15 targets there, I got 15 optical distances coming back into the interferometer, and as a result, depending on the optical path difference and the chirp rate, I generate for each one of those targets a unique beat frequency. And from that beat frequency, I can determine the distance and I can see how it's moving about. And you can see at the bottom, the top right there, you can see there's the frequency of the laser on the y-axis in time. If I've got a delay in the arm of the interferometer, I achieve a difference in the delay in the actual tuning from one arm to the other, and that difference drives through a fixed beat frequency. And that's where you can determine the distance with. Okay, so it's very simple. If I go more one target, I have a number of optical path difference, which then creates its own beat frequency. And that's essentially what is driving a lot of the applications at the moment for aerospace. So the advantage here, you've got a robust system, many channels in the one instrument, whereas fringe counting would require separate, say, Renish or ML10 systems. Each one have its own fringe counter. It's impossible to set up and highly costly. It's actually an absolute distance measurement as well. So with the standard fringe counting, once you beam break, if you actually cut the beam off, you don't know where you are. Whereas with this, because it's it measures the actual optical path difference, not just count the number of fringes from a given point, you actually know if you beam break it, you can still work out exactly where you are from the waist down. There's no synthetic wavelength. The accuracy, typically on these systems, I mean, you might find the fringe counting technique gets you to 1 part in a billion, but for most of these applications for Boeing, they're really looking at about 1 micron in a meter. So that's 1 ppm. So that's where they sort of like to be at. So this technology can achieve that. But one of the challenges I said down by there is target motion. So if you've got something which is vibrating around, then obviously that causes a problem. So what we've done is, if you imagine you've got a target now, which is like there in space, you've got light coming back and it's vibrating around because of all the noise. What that does, it effectively, you've got the beat frequency, what it does, it effectively phase modulates the beat frequency. Now you might have come across in telecoms where you've got phase modulation, frequency modulation. This creates a phase modulation. And that phase modulation is like, if you remember the Bessel sidebands, you create sidebands at the frequency of the modulation either side, and that's essentially broadens the spectrum. So vibration effectively phase modulates the beat frequency, which then broadens the spectrum so you get less resolution. So you can't see where you are, so the accuracy drops off. So what we've decided to do here is if we use a laser which chirps upwards, that's a normal chirp direction, and at the same time we have a laser which chirps downwards. What you find is when you multiply the outputs from the two together, so you do this electrically, but this is very similar to doing the sum and difference using a second harmonic generation, for instance, right? Using a nonlinear process, which just happens to be in this case, it's a detector because it gives you a signal proportion E squared. If I multiply those two together, then what I do is I separate those frequency terms out. So I separate the vibration, assuming it's a sinusoidal, from the actual beat frequency, which has been generated by the chirp. So you separate it, so you get the sum and difference of these frequencies coming through. And because you can do that, because you've got an opposite direction of the chirp, it allows you to cancel out the vibration in one component. And the vibration comes through as a very low frequency component, which can be filtered out. It's almost close to DC. You can filter it out. So your beat frequency is in gigahertz. You separate out the vibration on its own to be close to DC, which you can filter out because of this nonlinear process we're using and multiplication. And then you got the signal itself on its own. So you completely take out in real time, right? So you can take this out in real time, you do the measurements, and the vibrations are completely eliminated. So the problem with that is as you can probably recognize. I've just said the tunable lasers are quite expensive, and I'm saying, look, let's have 2 of them, right? Let's get 2 of these in there so we can perhaps reduce the cost through volume. It's not going to happen because these guys like to make money off the lasers. So it's going to cost you a fortune to do this. Equally, if you imagine you've got 2 tunable lasers, you've got to get exact tracking of the down chirp with the up chirp. And if you don't get exact tracking, and all you're seeing is the control loop, which is controlling one laser relative to the other, all you're seeing is the noise of the control loop. So that's going to dog the system. So it's not practical. So the only way you've got to do this, you've got to solve the cost, and you've got to solve the problems of doing the control feedback, and that's something which is instantaneous and generated for free. So what we've decided to do, I don't know if you come across 4-wave mixing. Now, 4-wave mixing was a big problem in telecoms. Right? When we were in Silicon Valley, you know, when you go down the optical fiber, you've got channel spaces of 50 gigahertz. Well, 50 gigahertz, you might have, say, 20 gigabits of data on each channel. But what you found is when they made the dispersion of the fiber 0, because that's what the drive in the late 90s, get the dispersion to 0, we'll maintain the quality of the signal. But when they did that, and then they did also alongside that, they had equal channel spacing, what they found was, because of 0 dispersion, they were getting crossed up between the channels through a phenomenon was 4-wave mixing. So what we did purposely towards the end of the 90s, people recognized this and said, wait a minute, don't make it 0 dispersion. We put a little dispersion in there, so we kill off this crosstalk. So we killed it off. We got rid of 4-wave mixing because of the equal channel spacing. So what we do here is, if you look at what we've got, you've got a pump, and you've got a fixed laser. And basically, as with 4-wave mixing, which is a Chi-3 effect, and it phase modulates. It's a bit like phase modulating the optical carriers due to these 2 components, the pump and the tunable laser. And essentially, as the red one goes to the right, which is your tunable laser, the 4-wave mixing effect with the pump puts the separation here, as you can see, is always the same. So if this goes up in frequency, in order for separation to be right, this means things the same. This goes down in frequency. So what that essentially means is we've got now a very nice technique, which means as I tune the one laser up in frequency, the 4-wave mixing will generate a component where the frequency is going exactly and instantaneously in the opposite direction by the right amount. There's no control tracking going on here. It's instantaneous in the scales we're looking at. So all of a sudden, this could be just a bit of nonlinear fiber, or it could be some waveguides which we're getting constructed by you guys, right, in Glasgow. So you need to have enough power density in the waveguides to be able to excite the 4-wave mixing to create an efficient conversion. So this is for free, and it's instantaneous, and opens up this possibility of vibration elimination. You can see there, just see where it goes? Distances, they're exactly tracking. So we've used 4-wave mixing in nonlinear fiber, and we've generated a down chirp laser almost for free. And what you can see there, you've got the red curve on the left-hand side. You can see it's wobbly, it's all over the place. This is all because of vibration coming through. That's the one output. The other output from the down chirp is the blue. And you can see what you've got there is noise again. But when we multiply the 2 signals, you can see the black line comes through, and it means that is then just the signal. There's no vibration in that signal at all. So you can now, with this technique, properly commercialized, you can go into Airbus or into any factory, you can use interferometric techniques to measure distances without worrying about all the vibrational effects, which means it opens up the possibility for these guys to really get on with the job and not get errors because of people moving around. So this is really quite powerful. There's an example here. We've got there's the wing in the factory. You can see we've got multiple targets. Remember, this technique can measure more than one target at any one time. You've got your beam splitter, and you basically just throw the light into space. And then you've got these targets, these small lenses, ball lenses, refracting it to reflecting light back in. And then you've got the detection system, which is basically looking at. Well, you've got 2 ways of looking at this. This at the moment is looking at it in a way that looks at the time domain, because that's what you see on the detector, and you do the FFT and multiply the FFTs. But you can see with the laser 1 is a tunable laser, which could be our new laser because it's now line width, it's robust, it's cheap. And then you've got a waveguide, which is what we're acquiring from Glasgow. We've got SOI waveguides, we've got 3.5 waveguides we want to get developed. And essentially, they're very small chips, say 10 millimeters long. The waveguides are very small. Sorry, do you want to take that photograph there? So the waveguides are very small, so you get the power density is very high to excite 4-wave mixing. This is an example here. We received some waveguides from you already, right, from Glasgow. And you can see you've got the silicon on top, silicon dioxide, and the waveguides are very, very small. So you're looking at 200 nanometers by about 500 nanometers, and you couple the light in, and the density is so high that you can achieve this excitation effects from Chi3, because this is Chi3, not Chi2. Chi2 is what drives second harmonic generation. It's an higher coefficient. Chi3 tends to be a bit lower, so you get higher intensities. On the bottom right there, you can see there's a photograph showing the wavelength and the conversion efficiency. And you can see it's flat at the top, but as it comes around, you can see it rolls off. Now, I mentioned this before. The reason it rolls off is because you've got dispersion effects creeping in as you go away in wavelength. And the dispersion basically means the Fourier-Mixing effect conversion drops off. Any dispersion here misaligns the tunable layers and the pump from each other, and the build-up you want is lost. It's not, I mean, it's parametric in the sense it isn't phase sensitive, but it's similar to Piplin, where you've got the periodic polling and you switch the nonlinearity so you can actually accumulate the second harmonic generation. But that's phase dependent. This is parametric, but you still get dispersion effects coming in, which drive off the efficiencies. So what we've done here is, on the right-hand side, we've shown the 3.5, similar dimensions. Silicon might be dogged by 2 photon effects because of the nature of the material. So you might get losses as you increase the power so much, maybe about 50 to 100 milliwatts. You start to get saturation. With 3.5, you can adjust the band gap because you can change the composition, and maybe you can get obviously the 2 photon effect outside of the region we're playing in. So we can actually play around a bit on the 3.5 to actually allow us to put even higher powers in, so we can get better conversion efficiencies ultimately coming through. There's again, you see the pictures there, and then the various styles and widths, and so we've modeled all this in using nonlinear Schrodinger equation to understand which is the best dimensions to work with, what length we can work with. Remember, the length of the waveguide itself might be 10 millimeters, but the ultimate limit is going to be a dispersion, the waveguide dispersion as you go further in length, or it could be scattering losses along the waveguide, which from you guys, I think you're saying it's about 1 dB per centimeter. You know, you are going to push these limits. But ideally, if you double the length of the waveguide, the conversion efficiency will go up by a factor of 4. So you can just see that nonlinear dependence on length again coming through. So you want to get longer lengths as best you can to reduce the powers required to get the same amount of Fourier mixing like at the other end. So there's a trade-off there. We're early stages of optimizing this device. This is a device we've got some samples from Glasgow. You can see because these waveguides are very small, we overlay with a polymer so that we can couple into a tapered collimator there, which then bounces like back and forth around the waveguide. The actual wave you want to light in, it bounces back and forth with a small change of angle each time, so that there's always a probability on the next interaction with the waveguide that it couples in. And this is a technique that's very powerful. If you didn't have this, you'd probably struggle to get 5% of the light into the waveguide. When you've got that tapered overlay polymer, it actually allows you to get couplings of the order of 50% at best. So it's a big breakthrough in terms of coupling light into these types of waveguides. So it works well for that one. And on the right-hand side, you can see we've got an array of waveguides, and we've coupled some light into them. And then you can see on the side here, we've actually used a SOI chip. You can see there's reasonably flat conversion efficiencies. The power levels are very low at the moment because we don't want to blow up the chips. So as you increase the power levels, the conversion efficiency actually improves dramatically. So these are consistent with the simulations which we've done. And for the power levels we get to, say, 20 dBm, we're looking at conversions of about 12 dB, I think, is that right? Something like that. So but these are low powers. And you see on the right-hand side the oscilloscope showing the idler and the Fourier mixing components, which then you can amplify using EDFAs to work through the system. An SOA can create it as well, because an SOA has a Chi3 effect through the gain changes of the device, because when you change the gain of the device, you can drive a Chi3. And what that does is it gives you good higher efficiencies, but the problem with SOAs is noise, right? SOAs are very noisy devices, so you don't use them unless you really have to. So that's why we don't want an SOA. The fiber is really good, but probably you need tens of kilometers of the fiber to generate enough Fourier mixing, so that's not really ideal. You want something which is small and compact, does the job, and we believe Fourier mixing in your waveguides will probably be the commercial solution ultimately. Let's optimize. Here we go there, you can see the overlay with what are we doing for time? Yeah, I best finish on it. And there's the waveguides, and then the way we couple the light from the fiber, we use a ball lens at the end of the fiber, which brings the mode down to about 2 or 3 microns into the taper waveguide, and then it couples ultimately from the polymer overlay waveguide taper into the actual waveguide, which is 200 nanometers by 500 nanometers. So you can see there's a staged approach, and we're achieving from fiber in to fiber out around about, at the moment, 10 dB loss, isn't it, right, from from in to out. So that's not bad when you consider Fresnel reflections and all. And that's 200 by 500 nanometer waveguide here. This is extremely small. So I think that's really impressive. Right. That's me done. So there's lots of things going on, but there's tunable lasers, there's 4-wave mixing, impacting both frequency swept interferometry for commercial applications and also for OCT. And that's what we're working on. There's other things we're working on, but I think that fits better into this program. Any questions? Question? Yeah. Yeah, go for it. Yeah. Yeah.
Yeah, sounds a good talk, Nigel. And quick question: you tried SOI? It's very narrow the waveguide. There is another 2 options. One is a lithium niobate film.
Okay.
It's similar structure. The top
right
is maybe 500 nanometer.
Okay.
For single mode, you can do 650 or something.
Okay.
And the other option would be silicon nitride.
Yeah, we have thought about silicon nitride. To be fair, we haven't thought about lithium niobate. I think something we need to look at. We need to look at what the Chi3 coefficient is.
Yes.
And if there's any other degradation effects there. But the silicon nitride one was definitely one on the cards because with silicon you got the 2 photon effect.
Yes.
And silicon nitride you don't. So it is an option we are looking into.
Yeah, but lithium niobate have very strong nonlinear. Efficient. Yeah. So
sure.
It would be the.
It's very similar to silicon, is it right? So it should be. Or is it?
No, really, to me.
It's more precise, is it? Okay.
Yeah.
Okay.
So you can do the 4-wave, the PPRN.
Yeah.
It's similar working theory.
Okay.
And this is the film, so you got a quite. You can make very small.
Okay.
Yeah. So there is a commercial wafers. Supplied by China.
Okay, but we were talking to Mark, about the silicon nitride the other day to see if that's a better option for us. So it's something we are definitely investigating. But lithium niobate, do you think lithium niobate would be a contender as well? So we haven't looked at lithium niobate.
Lithium depends what's your laser density in the waveguide. Yeah, usually it would be okay. And because they use for the telecom for a long time. So
absolutely, I'm aware of that. Yeah.
Yes.
But perhaps I'm not aware of being used at this sort of dimensions. 500 by 200 nanometers. Normally it's the order of micron.
But the coupling loss, it's quite high to me. You mentioned the 10 dB is including the propagation loss plus
propagation loss, coupling in, and then coupling out.
Yeah.
So it contains every step in there. I mean, we think we can do better than that. Probably, what do you reckon, Kyle? About 8 dB in total, if we tighten it. So there's improvements that can be made. Yeah.
Okay.
Thank you very much for that.
We're
definitely looking at silicon nitride. But if you got information on the lithium niobate, that'd be useful.
Okay.
Thank you very much.
Sure.
Any other questions? Okay. Right. If that's the case, we'll go on to the next talk, right? I think we got